In this video, I introduce a Kneser-Ney background language model. Kneser-Ney background language model is one of popular smoothing techniques, since the actual number of sequences is much larger than number in the corpus. Kneser-Ney model uses a smoothing technique to discount the probability of seen words and give a non-zero probability to unseen words in the corpus, so that the probability accuracy of estimating words is improved. Background language model is written in this formulation. P is the probability of a current word for given history H. Alpha is the probability for n-gram model. Beta is the probability for n-1 gram model. Gamma is normalization factor to guarantee sum of this probability to be unity. Gamma is determined by alpha beta. If beta is equal to the probability for n-1 gram, which is called Kneser-Ney basic language model. Now we introduce a modified Kneser-Ney background language model in which we calculate beta using the marginal distribution. Suppose alpha is known for n gram with n larger than 0. The task is to determine beta first and then gamma. Using definition of marginal distribution, the probability of n-1 gram is estimated through margin over words G. G has the same size as H. G includes two parts. One is n-1 gram, and the first word is unseen word. So we use the marginal distribution. We calculate this P by using this margin of this joint probability over this history's G. And then we use the chain rule to use these two terms to express this joint probability. If this G is independent of this H, this P is 0. So we only care the G with hat equal to H with hat. And then we use alpha and beta to substitute this P to calculate this margin of joint probability over this G. And this first term is related to alpha, and the second term related to beta. Because beta is no relation with this G, so we moved this beta out of this sum. And then we calculate the normalized beta function here. To calculate the beta, we need to calculate this P and this product of alpha and P. We select alpha with discounting factor D. So this alpha is in this formulation. Assume maximum likelihood estimate for marginal distributions. And then we got this probability of n-1 gram language model in this normalized formulation, and this P in this normalized formulation. We substitute this 2P and alpha into the formulation above, and using this product of this alpha and P, we cancel this denominator and this numerator. Because all the terms here include the same denominator, so we can cancel each other. And then we get this normalized beta. Because this is the number for the n-1 gram, and this for the number of n gram, but we are calculating the margin over the first unseen word. That means this first term equal to this one. They can cancel each other. We only leave this D. If we define this n minus is the margin of this D over this G. This G is the first word, unseen word here. And then we define the corresponding normalization factor. that is equal to the margin of this n plus over the current voltage W. We got this normalized beta formulation. If we compare with the Kneser-Ney basic language model, they have a big difference. So we use this beta to calculate this gamma, use gamma, alpha, and beta to calculate the probability of the current word for given the history H. For more details, please check with this reference. Thank you. Bye.